think most of you have heard of what tropical cyclogenesis means, or you have heard about it whenever we discuss tropical cyclones that are already born. And that tends to be the tricky part, that you can always find necessary conditions for cyclogenesis, or a birth of an incipient vortex that can survive and evolve into a tropical cyclone. And most often the tropical cyclone or a tropical storm is born, and then you have to go back and see the conditions in which it may have born. So there is really never any real evidence of going from the seed that may have been put down by these various conditions that we will look at that favor cyclogenesis and how it survives. So it's a bit of a tricky situation. We talked about this before, the subtropical ridge and how the cyclones get steered. And when you look at the regions where they begin to appear from, let's say, a tropical disturbance into a tropical depression, storm and hurricane, and then may intensify into a major hurricane or not, and so on and so forth. It may go into the Gulf of Mexico and come out, or it might go off into the extratropics and do the extratropical transition, etc., etc., etc. So we can always find necessary conditions for the formation of a tropical cyclone, and they are not always sufficient conditions. So this is where the difficulties are. So in terms of predictions, it comes down to looking at whether the models which have been doing so well with the cyclone predictions, even though we don't understand many of the processes, whether they can also begin to predict cyclogenesis. And there is some evidence that this is happening in the Indian Ocean. The India Meteorology Department has managed to predict couple of, maybe more than a week ahead, that a cyclone will be born, which is essentially a prediction of a cyclogenesis. So 6 features of the large-scale subtropics were identified by Bill Gray as necessary but not sufficient conditions for tropical cyclogenesis. So sufficient ocean thermal energy for driving the Carnot cycle. We need the heat content above 26 degrees centigrade down to a depth of 60 meters, but this is again empirical. Enhanced mid-tropospheric relative humidity at 700 hectopascal, which is required to fire up the convection and feed the energy. Conditional instability, so that the convection can be triggered and grown into to intensify the incipient vortex. Enhanced lower tropospheric relative vorticity. So we are this is why we are always away from the equator, where the planetary vorticity goes to 0, and moving around doesn't make much difference. But once you go off the equator into the tropics, any movement of an incipient vorticity, incipient vortex, is going to interact with the planetary vorticity, and the absolute vorticity, which we will look at later, will begin to respond with cyclonic circulation. So the enhanced lower troposphere relative vorticity is critical, and it can be set down by these various processes that are discussed in under cyclogenesis. Weak vertical shear of the horizontal winds at the genesis site. This is often necessary, but once the cyclone is born, then it tends to be a little different, where some level of vorticity may allow the cyclone to intensify, but very strong, some level of vertical shear may allow the cyclone to intensify, whereas very strong shear tends to chop off the energy and basically not allow the cyclone to grow and intensify. So at the genesis site, when it's still, the incipient disturbance is still trying to grow, then you need relatively weak vertical shear. Displacement of at least 5 degree latitude away from the equator, as I said, when you combine with this condition of relative vorticity, that means the relative plus planetary vorticity will together begin to do vorticity conservation, angular momentum, convergence, vertical motion, and so on, that are necessary for it to grow. So in a simple way, vertical wind shear calculation is done this way. You have upper level here at 6 kilometers, 20 meter per second going, let's say, towards the northeast, whereas here at the lower level you have 10 meter per second going towards the northwest. Okay, so this vertical shear of 25 meter per second, yeah, 30 divided by 6, no, never mind, just it should be 30 if I'm not mistaken, but please check it. I don't know why I suddenly get confused with these things. But so vertical shear in any case is bad for allowing the incipient vortex to grow. Monthly diagnostics are looking at the different cyclogenetic regions. So here you are looking at the Northwest Pacific, which we'll come back and look at more specifically in terms of the monsoon trough and the ITCZ. You look at the July vertical wind shear and September SST, December vertical wind shear here slightly to the east around the date line, and February SST. So you can see that the weak vertical wind shear here is favorable. It's order 10 meter per second. This is in meter per second. December vertical shear is weak here. February SST is favorable here with warm SSTs, but remember we need heat content. And September SST is favorable further to the east over here. Okay, so there are obviously cyclogenesis seasons. The hurricane season or the North Atlantic starts on June 1st officially and goes to November 30th, but you can have obviously earlier cyclones. Now it's happening and obviously we are always trying to see if that's related to global warming and so on, and it can happen later than November 30th, and I think other than February and March there have been cyclones in all months at some point or the other. And the cyclone season in the Pacific is much more widespread throughout the year. The cyclone season in the North Indian Ocean is split by the monsoon season into pre-monsoon and post-monsoon seasons and so on. So there you know that these cyclogenetic favorable factors matter a lot. So Genesis potential index is defined. We will look at it a little bit later on. And now people are often redefining them. So here several indices are compared, including a new one that is defined in this paper called GPI Ocean, Genesis Potential Index, that includes the ocean. You think that's intuitive, but not always included before. Obviously when people publish a new index, they argue that their index is better than the older ones. But the main thing I would notice here is that when you look at Genesis Potential Index over the West Pacific, the ocean, and various earlier studies, you can see that there are differences, and here Genesis potential is negative in some of them and positive when the ocean is included. So the idea is always to reprocess past cyclones to try to explain why GPI before may have been missed in explaining the cyclone that was born. Okay, so sorry, that was a bit fast, but I don't want to make any further point than the fact that once you have necessary conditions, you can develop a Genesis potential index, and then that index tends to get improved by people as they reprocess the longer time series and so on. Thus, the necessary but not sufficient criteria for tropical cyclogenesis may be summarized as the ability to support deep convection in the presence of low-level absolute vorticity maximum. Okay. The low-level vorticity maximum reduces the local Rossby radius of deformation, focusing the convective heating locally. Okay, we will define the Rossby radius of deformation. I forgot if we have already done it, but we will, or we have already done it. But in the tropics, the radius of deformation tends to be large because there is an F in the denominator. And that means that the perturbation or the disturbance unless it's larger than the Rossby radius of deformation, it can get dissipated by the environmental conditions. But if it is larger than the Rossby radius of deformation, then the circulation tends to adjust to the disturbance. So what are the processes that can reduce this intrinsically large Rossby radius of deformation in the tropics? Turns out that low-level vorticity maximum can do that. Okay, here is the Rossby radius of deformation for a continuously stratified fluid. It is basically a balance between stratification and rotational effects. We will see what it is in more detail. So it is defined as NH over F0, where N is the Brent-Vesala frequency, the static stability frequency parameter. When the parcel is perturbed, if it's unstable, it'll keep going in the same direction. If it's stable, it'll oscillate and come back to rest. H is the depth of the system, and F0 is the Coriolis parameter. For a weather system with large relative vorticity, such as a tropical cyclone, and LR can be generalized as NH over zeta plus F0, which is the absolute vorticity, and hence this, if this is large, obviously this will get reduced, which favors the survival and evolution of the cyclone. Okay, so there it is. I will explain it in the next podcast, but we will leave this here as an introduction to tropical cyclogenesis, and we will look at specific processes which put down either the initial vorticity or reduce the background conditions. For example, El Nino and La Nina tend to modulate cyclogenesis. MJOs do that. There are mesoscale convective systems which can put down initial disturbance. There are equatorial waves who do that, and so on. So we will look at all those details in the following podcasts.